Okay, another problem from ray optics. This one is about something I found in Wikipedia called a Poro Prism. So the definition is that it consists of a block of material shaped like a right geometric prism with a right angle, triangular end faces. In operation, light enters the large rectangular face of the prism, undergoes total internal reflection twice from the slope faces, and exits again through the large rectangular face. If you don't know what this looks like, that description might be hard to understand. So this is what it looks like. So it's a prism. It has a right angle and two 45-degree angles. Let's say that light comes in, that we orient this thing with a long side perpendicular or a vertical, and the light comes in horizontal. So the light is going to go through the prism, through the first or the front surface of the prism, is going to hit the back surface, as you can see there. The idea is that the light is going to experience total internal reflection on that surface. Then it hits the second surface and it again experiences total internal reflection. Notice that the way we set up this thing, since it has a 90-degree and a 45-degree angle there, those two angles are 45 degrees. Therefore, this angle is also 45. So that means that the light ray that hits that back surface is making a 90-degree turn. So now it's going vertical, it's become perfectly vertical and going down. And when it hits the bottom surface, the same kind of reflection is going to happen. The total internal reflection will happen on that surface. All the angles are 45, and again the light ray is going to experience a 90-degree turn, which is going to make it horizontal again. So with this kind of setup, the light comes in and it gets reflected and goes back the same way it came. So there are multiple applications for a Poro Prism, and one of them is in binoculars. Binoculars use a set of Poro Prisms inside to change the direction in which the light comes in, and so there's many other applications. This is a very useful material or optical device. All right. So what is the question here? Well, that angle is also 45, as I said. I'm going to assume in this problem that the light is coming from air, that the index of refraction of the prism is n. And my question to you is, what is the minimum n for a Poro Prism to work? That is, for a Poro Prism to be able to have total internal reflection on both surfaces. So that is the question. So let's start by reminding ourselves about total internal reflection. The idea is that when light goes from a high index of refraction to a low index of refraction, there is a minimum angle called theta critical, theta c, such that if the angle of incidence is bigger than the theta critical, equal or bigger, we have complete reflection and light does not go to the other material. So the interface acts as a mirror. So in this, just a picture here, I have two materials. That's the normal to the interface between the two materials. That's the angle or critical angle. So the two materials, depending on their n, the index of refraction, let's say that the top material has an index of refraction n, the bottom has 1. So there is something called a critical angle. And if you send light rays with an angle bigger than that, with an angle of incidence bigger than the critical angle, the light ray gets completely reflected. Total internal reflection. But if the light ray that you send is at an angle less than the critical angle, then the light ray actually manages to go through the interface, gets refracted, and moves into the second material, in this case n equal 1. So that's the idea with the critical angle. So the idea with the prism is that we want the index of refraction to be such that for an angle of incidence of 45 degrees, as you can see in the Poro Prism, the angle of incidence in the surface on the back, on the top one, is 45 degrees. So we want that the angle of incidence, which is 45 degrees, needs to be bigger or equal to the critical angle for this situation, which is n going into 1, and index of refraction n going into index of refraction 1. So we have 45 degrees should be bigger or equal than the theta critical for this prism. So notice that if there is total internal reflection in the top surface, there will also be total internal reflection on the back surface. All the angles are the same. The angle of incidence also is 45 for the second surface. So if there was total internal reflection on the top surface, there should also be at the bottom. So if the equation is satisfied that 45 degrees is bigger or equal than the theta critical for this prism, then we're in good shape. So what is the equation for theta critical? For the interface between n and 1, so that is the inverse sine of 1 over n. If you recall, that was discussed in previous videos. So we want 45 degrees to be bigger or equal than the inverse sine of 1 over n. So if we take the sine on both sides, sine of 45 degrees should be bigger or equal than 1 over n. And solving for n, we get that n should be bigger or equal than 1 over sine of 45 degrees. The sine of 45 degrees is square root of 2 divided by 2. So if we flip that, because we have 1 over the sine of 45, we get 2 over square root of 2, which is the same as the square root of 2. And this equation is saying that for this prism to work, the index of refraction should be bigger or equal than the square root of 2. So the smallest value that we can have, therefore, is when n is equal to square root of 2, and that gives us a minimum n of 1.41 for a Poro prism to work. Fortunately, most solid transparent materials have an n that is bigger than that, so glass in particular would work fine. All right, so this is it. I'll see you in the next one.